This project is the FPV Aid laptimer sensor, designed to be placed near the start and finish gate of an FPV racetrack to detect when a drone passes the line. Its main purpose is to notify the FPV Aid ground station whenever a drone crosses the start or finish point, enabling accurate lap timing and race tracking. The sensor communicates wirelessly with the ground station using LoRa, providing reliable long-range connectivity for race environments. Like every electronics project, everything starts with the schematic and PCB design. I'm using KiCad-free software to design new version of laptimer sensor hardware. The goal of this hardware revision is to eliminate the need for a separate 3S UPS as the power source, reduce the overall device size, and improve system integration. This version adds onboard non-volatile memory for persistent setting storage, replaces the power monitoring integrated circuit, and upgrades the main microcontroller from the Raspberry Pi Pico 2350 to the Raspberry Pi Pico 2354, while removing the need for external flash memory. It also introduces seamless battery hot swap support between USB power and any lithium polymer battery source, ranging from 4 volts to 30 volts, improving flexibility and reliability in real-world use. Additionally, 8 megabytes of pseudo-static RAM have been included for future expansion. While it is not currently utilized, it provides room for upcoming features and can be ignored for now. For this iteration, I decided to manufacture the printed circuit boards in Europe and chose Eisler as the manufacturer. It offers a good balance between quality and cost, which makes it well suited for hobby projects like this one. Since this is still a new hardware revision, I decided not to use assembly services and instead assembled the boards manually. This makes it easier to catch design issues early and adjust the hardware if needed. Once the design is proven and larger quantities are required, or when manual assembly becomes too time-consuming, I would also consider ordering the boards with full assembly. After almost 3 weeks of waiting, the package finally arrived with my printed circuit boards and assembly stencils. These are 4-layer boards with an Electroless nickel immersion gold surface finish. Most of the signal traces are routed on the top layer, while all layers include copper pores to help dissipate heat from the RX video receiver modules. After a quick visual inspection, it's time to clear half a day from my schedule and get started with the assembly. First, we need to align the stencil with the printed circuit board and apply the solder paste. After inspecting the solder paste application, we can move on to component placement. And boy, oh boy, manually placing 0402 components does not mix well with my caffeine consumption levels. Placing this many components takes a lot of time, and after taking a dinner break, it was clear that the solder paste had already started to dry out and lose its tackiness. That makes it harder and harder to place components and keep them in position. But once the reflow process starts, heat and solder surface tension should work their magic. The magic moment is when the solder starts to melt and pull the components into place. Even though I'm showing you a sped-up version, this really deserves to be seen in slow motion. It's one of the most satisfying processes to watch. As always, when you get distracted filming the process, you forget to keep an eye on the components that don't quite pull into place as they should. And then you pay the price by having to rework a few of them with a hot air station. Not my proudest moment, but it's all part of the manual assembly process. Now it's time to solder XT30 socket for LiPo battery. At this point, after checking that there were no shorts, it was time to power up the printed circuit board. We don't have all the peripherals installed yet, but we can already test whether the brain of the board, the microcontroller unit, is alive. Now that we have a functioning brain, it's time to flip the board over, add the remaining modules, and complete the assembly. Next, we need to solder on the LoRa module and a passive buzzer for some audible feedback. And now it's time to add the last two components, the RX5808 video receivers. These chunky modules are the most power-hungry parts of the board, and as a result, they generate the most heat. Some of the pads, especially ground, are not that easy to solder with the small soldering iron tip I was using. Sorry, I was a bit lazy and already getting tired. There are 4 layers of copper stitched together with vias, and they really do act as a heatsink, exactly as intended. The thermal reliefs help, but a larger soldering iron tip would make the job much more efficient. And with that, the assembly is complete. I'm back in my home office and ready to test the firmware I wrote for the hardware self-test. This firmware was written while the printed circuit boards were still in manufacturing. Now it's time to boot it up, connect the OLED screen, and see the results. Looks like all 11 out of 11 peripheral hardware tests passed. At this point, we can be confident there were no mistakes in the printed circuit board design or manufacturing. The final step is to upload the updated laptimer firmware and confirm that it connects to and initializes correctly with the FPV-8 ground station. It does. Great success. That concludes the electronics part of this project. The next step is engineering an enclosure, and after that, this iteration of the FPV-8 laptimer hardware will be complete. Thanks for watching. Like and subscribe, and I'll see you at practice sessions or official FPV races.